All right, let's dive into a genuine cosmic mystery. We're going to be talking about our very own sun and a kind of secret speed limit that keeps its incredible power from going completely off the rails.
So you probably know the sun has this sort of heartbeat, right? That famous 11-year cycle where sunspots and solar flares ramp up and then die down. It is an unbelievably powerful engine. But have you ever stopped to think, what's stopping it from just spinning faster and faster and faster until it spirals completely out of control?
You know, this is actually one of the great mysteries in solar physics. The sun's magnetic cycle, it's driven by a feedback loop. So in theory, a stronger cycle should create an even stronger one next time, and so on, leading to this runaway growth. But it doesn't do that. Something out there is acting like a thermostat, or maybe a brake, and today we're going to figure out what it is.
Okay, so like any good detective story, when you have a mystery, you need suspects. And for decades, scientists have had two prime suspects for what's putting the brakes on the sun's cycle. So let's meet them. And here they are: tilt quenching versus latitude quenching. Now, these names might sound a little technical, but the ideas behind them are actually pretty straightforward. Think of it like this. Tilt quenching is the idea that when a cycle gets really strong, the magnetic regions kind of flatten out, making them less powerful. It's like a boxer weakening their own punch. Latitude quenching, on the other hand, is all about location. It suggests that in stronger cycles, the action happens farther away from the equator. That's kind of like missing the target entirely. Let's look a little closer at our first suspect. Tilt quenching is all about the angle of these active regions. See, normally, these tilted magnetic spots are fantastic at building up the energy for the next solar cycle. But this theory says that when a cycle gets really strong, that tilt just flattens out, and that weakens its ability to see the future cycle. It's a really clever self-regulating mechanism, all based on that change in angle.
Now for our second suspect, latitude quenching. This one is all about one thing: location, location, location. Scientists have noticed that in more powerful solar cycles, the sunspots and active regions tend to pop up further away from the sun's equator. And according to this theory, that extra distance makes it way harder for their magnetic energy to drift to the poles where it's needed to fuel the next cycle. So this is a brake based purely on geography.
So we've got two great theories, two solid suspects. But how on earth do you prove which one is right? Well, you need evidence. And to get it, a team of scientists had to become basically solar detectives, digging through over a century of astronomical data just to rebuild the sun's magnetic past. And believe me, this was no small job. First, they had to take these old solar maps, made using a specific kind of calcium light dating all the way back to 1923. From those, they identified all the active regions. Then, they had to painstakingly match those spots with hand-drawn sunspot measurements from the Mount Wilson Observatory, just to figure out which end was magnetic north and which was south. And finally, they calibrated the whole thing to create this one amazing, comprehensive 62-year magnetic database.
And you can really see the transformation right here. They took these raw historical maps, which are really just patterns of light and dark, and through all that incredible work, they turned them into modern magnetic maps. They literally turned old photographs into a powerful scientific tool. And the result of all that detective work is this beautiful chart, a 62-year history of the sun's magnetic activity. It perfectly shows that iconic butterfly pattern, where sunspots show up at the mid-latitudes and then drift towards the equator as the cycle goes on. This unique dataset held all the clues they needed.
Okay, so the historical database is built. The stage is set. It is finally time to put our two suspects on trial and see which theory actually holds up when you confront it with the cold, hard evidence. And right out of the gate, this incredible new database offered up the first major clue in the case. Check this out. This chart shows how strongly each of our suspects correlates with the strength of a solar cycle. And wow, look at latitude quenching. It has a correlation of 0.88. Now, in statistics, that is a very strong link. It basically means the stronger the cycle, the higher the latitude of the sunspots, exactly what the theory predicts. But tilt quenching? A much weaker connection. The data is pretty clearly pointing to one suspect over the other here.
So this was a really powerful piece of evidence, for sure, but it wasn't quite the smoking gun. For the definitive proof, the scientists turned from the past to the future, using a powerful computer model to simulate the sun's behavior.
Now, this simulation was designed to find one key value, the size of something called the dynamo effectivity range. You can think of it as the sweet spot near the equator, where a sunspot has the absolute most influence on the next solar cycle. And the model that best matched the real-world data found this sweet spot to be incredibly narrow.
How narrow? Less than 10 degrees. So why is that number such a big deal? Because a value that low is the classic telltale signature of latitude quenching. That's the whole point of that mechanism. It works by moving the active regions out of this super narrow crucial zone. It was the final piece of the puzzle.
So the direct data pointed to it, the computer simulation confirmed it, the investigation was officially over, and it was finally time for the verdict.
And the conclusion is this, stated perfectly clearly by the authors of the study themselves. We propose that latitude quenching is more important than tilt quenching in regulating the sun's polar field production. I mean, case closed.
So let's just quickly recap this whole stellar detective story. The mystery was, what puts the brakes on the sun's 11-year cycle? The two main suspects were tilt quenching versus latitude quenching. The clues came from this heroic effort to build a 62-year magnetic dataset from old records, combined with some seriously powerful computer models. And the verdict is in, it's latitude quenching. Where the sunspots appear, that's the sun's primary speed limit.
It's really an amazing discovery. We finally found the sun's secret speed limit. But of course, solving one mystery just makes you wonder, what other incredible secrets is our star still hiding from us?